is a primary, so it says transformer is connected, switch is closed momentarily and then open. So they close it. So only for that split second when they're closing it, there's a magnetic field being created. So the magnetic field forms, and this coil is in that magnetic field. So it will experience a change in magnetic flux, but only while these lines are being formed. So it will have it. So if we again, or I always go to my flux graph first. So this will have a change in flux for a split second. So it will go up, it will come down. So it will just literally do that. It will have a very quick thing and then it will be gone. Then, as it might not be that shape, but I'm just showing it something. Okay, then while it's disappearing, so when you're opening the switch, as soon as you're opening the switch, these lines will be disappearing. So as they are disappearing, then there's a change in flux again. But while the current was running, there's no change in flux because it is a battery that needs, and this is the one reason why a transformer has to be AC. So when you see a transformer, it has to have an AC source. Look for that. Because if it has a battery, it's just going to give you a split second change in flux as it's switched on. So this one will have a split second induced voltage and induced current. And then when you open the switch again, it will be in the other direction. So it will be literally up, and then down. So when we're looking at the options, because now it's disappearing. Oh, I see. They're really trying to confuse you here. So as you switching it on, ooh, what are they doing? Which of the graphs correctly shows the variations against time of the readings on V1 and V2 respectively? V1, oh, okay. So V1 is going to be switched on, it's going to stay on, and then it's going to be switched off. Yo, I don't see an option. I want it to be this one, but I don't like that it's in the same direction. Because when you're switching it off, the field lines are disappearing. So I want the answer to be this one and then this one. Okay, so I'm hoping that you're seeing that the rubbish are these two. Okay, so these two are not options because they are giving us nothing. Yeah, so those are not right. So it is one of these two, but I am not happy that it's so for. So it's definitely A. It's definitely not B because the answer is it has to go one direction, then the other direction, not because it's alternating current, but because the lines are appearing, forming a current in the one direction or voltage or change in flux and then disappearing, and as they are disappearing it's the opposite change in flux, so it's definitely this one. Yeah, I guess, yeah, they're giving because the reason why it's just gradually going up and then gradually coming down is because it doesn't immediately, there's not an immediate flow of current, so that's probably why they didn't want B. But it is a direct current, so it doesn't take that long. It's like a split second for the current to start flowing. So V1 should have an immediate voltage in it, but this is definitely the most correct option. Is then A. They I guess they didn't give us a time scale, so that would be in a split second that these field lines are being created. So that's maybe why they're giving it some time for that voltage to form. Then, yeah, when the voltage is constant, then there's no change in flux for the secondary coil, and that's why it's zero, and then it's going in the other direction because it's disappearing. So I would say it's A. Are you happy with that one? This one we have definitely not done. Um, Two current carrying conductors, but they are trying to catch you because I'm going to go straight to the answer because they say to the question. It says, which of the following statements about the force that the current carrying conductor A exerts on current carrying conductor B is correct? So, what do you know about the forces between those wires before you even look at anything else in the question? They must be the same. So these two are going to be the rubbish. Great. Because it's Newton's third law. If A exerts a force on B, then B exerts a force on A. So Newton's third law still is there all the time. So now we just need to look at the direction, and they've given us. So the 10I and the I was just there to confuse you. So it's definitely not going to be less. Then, which of the following statements, sorry, they're giving us the current. So now we just have to look at which direction the wire is going to experience a force. And this one is a bit tricky because you need to realize that there's a field formed, and it's easier when they're drawing it like this. If we're saying this is into the page and this is out of the page, because if this is into the page and this is out of the page, then we can kind of see it easier because into the page would be a cross. Out of the page would be a dot. So if we now go and we use our right-hand rule for a straight conductor, remember these are straight conductors. So what you will do is for this one, if it's into the page, you're going to stick your thumb into the page. So which direction will the magnetic field be around this one? You remember to use your right hand, so it's going into the page. So if you stick your thumb into the page, which direction is your fingers going? Mine's going clockwise. Are you using your right hand? Okay, so right hand into the page. So your thumb goes into the page. Then you take your curled finger. So it's not the slap rule. It's the one where you have your thumb and your fingers for straight. So you hold the conductor as if it's a straight wire. You push your thumb into the page and you curling your fingers around. Are you getting clockwise now? Okay. So remember when it's a straight conductor, there are not three things. There are only two things. There's a wire, and the wire is gets a magnetic field around it. So it is the motor effect, but there's two input currents. So this one, because it's going into the page, the magnetic field is going to go clockwise, the B field there. Then if we do it for the top one, it's also going to have a circular magnetic field. Obviously, if they really wanted you to draw this, then you'll draw those further apart to show that the field is weaker. But then for that one, now we're going to, so just check your right hand rule again. So now your thumb is coming at your face, and then your finger should be curling anti-clockwise. Are you getting that now? Okay, so this is going anti-clockwise. Now what you must look at here in the middle. In the middle, they're going in the same direction. So the B field for the top wire is going to the right, and the B field for the bottom wire is going to the right as well. So the red one is going to the right as well. So that means here between the two wires, there's a higher magnetic flux density. There's an increase in magnetic flux density. And as soon as there's an increase, remember what we said, always the wire will always experience a force from a high magnetic flux density to a low magnetic flux density. So then the wires will actually repel each other. So this one will be pushed upwards, will experience an upward force, but that force is the same as what this one will experience, but that one will experience a downward force. And they're asking us for the force on B. So because they are going to repel each other, the B is going to be pushed downwards. So the answer should be okay. So a shortcut for these ones where they and yeah, I'm not a fan of shortcuts. You know now why this happens, but for a shortcut, if it's a multiple choice, because you don't want to spend so much time on the multiple choice, is that if the currents are flowing in opposite directions, I know it sounds weird because normally opposite poles attract. But it isn't because it's not opposite poles, remember? It's the magnetic fields that are being created around each of them. So when the current flows in opposite directions, the magnetic flux density in the middle will always be a higher magnetic flux density. And that would mean that they're always going to repel each other. So the force will always be away from each other. If the currents are going in the same direction, so if you have a current going that way and a current going that way, doesn't matter up, down, left, right, but as soon as the currents are going in the same direction, then in the middle, these lines here would be going in opposite directions. So that means in the middle, we're going to have a lower magnetic flux density, which would mean in this case, the force that these wires will experience is going to be towards each other. So they will attract each other. Does this make sense? Okay. So it's not just opposite attract. Please don't think about it like that. You have to remember that it comes from here. It's quite tricky. It looks simple, but it so a shortcut makes it simple, but you need to understand that it comes from there because they often ask to explain why. Then remember that first magic sentence. Then you're going to say there are two magnetic fields interacting with each other, and those magnetic fields create low magnetic flux density, high magnetic flux density, causing the wire to move or experience a force towards the lower magnetic flux density. Okay, transformer again. Primary and secondary coil connected ammeters current is turned on. Okay, so they're using a DC source again. So please remember in a transformer we don't have a DC source. We would like an AC source. So this is bad because because they say current in the primary coil is turned on using a DC source. So you will see a split second current and then it will be gone because there will just be in the secondary coil, because there will just be a change in flux again, like that first one. There will only be a change in flux as you're switching it on. So this time you're not even switching it off. So you will just get that. The secondary coil will just have a quick change in flux. So it will have a quick current flowing in it and then it will be gone. Okay, then what would be observed in the ammeter connected to the secondary side? So we're looking for that answer. No reading is not right. If the DC source was already on, then this would be right. But they say it's turned on. So for that split second when it's turned on, there is a change in flux. And if there is a change in flux for a split second, a, there will be a split second current in the secondary coil. So it says the reading reaches a maximum returns to zero. So this could be an option. The reading reaches a constant average. No. Sneezing constant doesn't work. And then the reading fluctuates between a maximum and minimum. No. So the fluctuating one would be if you have AC, which is what we should have for a transformer. But we don't have AC. So because we don't have AC, we cannot have fluctuating. So when they say fluctuating, this is the one that people are used to seeing. So this is what they are looking for. But to have this, we have to, in the primary coil, have an AC source. So the only one that it could be is then B, because it's just going to turn on quick and then go away because of the DC. So please look out. It looks as if you guys have done a lot of questions on DC for a transformer with a DC source. So look out for DC sources in your prelim. When is your prelim? I know I've asked, but I just want to make a note of it. Okay. Monday now. Oh wow, okay. Did you do law? You have done last year's paper, right? Okay. Alrighty. So the coils of the AC generator do they belong to the cluster that sets the papers together? Your school There is a Natal cluster there that sets paper. I'll get their prelim from last year, the Natal clusters paper, that you can maybe do that. Okay. The coils of an AC generator make one complete rotation. So this is an AC generator. The graph for the EMF is shown. Okay. So that's normal. So that is what any generator, a normal generator, would look like. Then they say position Q. Now remember, for position Q, if the EMF is a zero, it means that the flux was a maximum. So if you had your magnetic field going like this, it would mean that if your coil is in this position, which is horizontal, oh, sorry, why always does that? When your coil is in a horizontal position, the flux is zero, okay, which means that your EMF would be a maximum. But if it's in the vertical position, so if it's standing up like this, going like that, then the flux is a maximum, so the EMF will be a minimum. So they say the position Q on the graph is obtained when the plane is, of the coil is at an angle of what to the magnetic field, and the magnitude of the flux is what. So yeah, so if the EMF is a maximum, so the quick one to spot the rubbish is if the EMF is a maximum, that would mean that the flux for these graphs is a minimum. So that's where it starts in this position where all the lines are going through that coil. So the flux would be a minimum. So yeah, when EMF is maximum, flux would be a minimum. So we know that it's either going to be this one or this one. Are you happy with that part? See now, minimum. I would. Can you go? The thing is, this is a confusing one because how can they say minimum? Yeah, so you're right. Minimum, you can't go lower than zero. So I don't know what they mean. If they are saying minimum is negative, that is very wrong. So the thing with the minimum, I wouldn't even want them to put that in there. There should be a maximum as well. Because if they're saying minimum and zero, for me, that is the same thing. But it's definitely zero. But yeah, that's a bit of a confusing one. But let's look at the angle now because the angle is then going to give it away. Because if they say the the magnetic field, the angle of what to the magnetic field, the plane of the coil is angle of what to the magnetic field. So if we're looking at this one here, so it's at an angle of 90 degrees to the magnetic field. So it's this one. So can you see that it's 90 degrees? Okay. So you can't use the equation here because the equation is not about the plane of the coil. The equation is about the normal. So that D1 is definitely there to confuse you. Because if they say the plane of the coil, it's this one here. It's the plane of the coil. So it's like a flat line going in to your page there. If they're saying, if we use the equation, BA cos theta, then we have to use the normal. And the angle between the normal and the magnetic field is there is zero because they're going in the same direction or 180. So then that's why D was definitely the distractor, the minimum and the 180. But the answer should be C. Do you understand why? Okay, so it's the plane of the coil and the magnetic field that forms 90 degrees with each other there. So you can't always use the equation. I actually never use the equation except if I want a shortcut in a multiple choice for values. But you don't have to be able to do calculations for this section anyway. Okay, so for this one, you need it's similar to that one that she had in the recent paper, where these two can both be moved. So if they can both be moved, it means that you need to look when is there a change in flux? So if you're taking both of them and you're moving them like this together, means you're moving this one and you're moving that one at the same time. There can be no change in flux because this magnetic field is stationary. So this is a stationary magnetic field. So it's always there. So the field lines are always there. And the only way you can change the flux that this one is experiencing is if you're moving them relative to one another. If you're not moving them relative to one another, there's no change in flux. So that's why to the left, and to the right must be wrong because that means we're just moving them like, oh, now I'm doing it wrong. I'm moving them like this. So nothing is changing. So the only way it could happen now, I can use this, is if I'm moving it like this. Because now, if you're looking those field lines crossing here, is if you're ignoring this magnet and you're saying, okay, now these field, if the magnet is moving towards the coil, now it's experiencing a change in flux, but not when they're moving together as one. So to the left, and to the right are the options that we're going to scratch out. So to the left, and to the right is not going to be our options. You happy with that? Okay, so now we just need to look at the current direction that they are giving us. And they're giving us a current that comes up and over. So if you're looking at the current here, the current is coming up and over the wire. So that means you're still going to use your right hand and you're curling your fingers from the back over to the front. So where do you get a north pole? On the right hand side, yes. So if this is a north pole, so they're telling us by giving us the arrows that there is a north pole here. So that means that the new magnetic field that we created because of the change in flux has a north pole there and it has a south pole. Yeah. So now we can see south and south would mean they are repelling each other. So if I want them to repel each other, what would the change be? Would they be moving towards each other or away from each other? Remember, you are opposing the change in flux. So the yeah. So you must be pushing them towards each other so that the reaction could be pushing them away from each other. So now we can look, they're asking about the magnet. So the magnet is being pushed to the right. So the answer then should be D. Happy? Okay. Okay, there's another one of these. So it's still induction, metal ring connected to the ammeter. Magnet is held. So as soon as it's held still, so again, there's my magnetic field lines as you drew them there. As it is held still, there's no change in magnetic flux. Therefore, there's no reading on the whatever that is. I guess it's a galvanometer. What do they say? What will be observed on the meter? Oh, it is an ammeter. They did say ammeter. When you see galvanometer, don't get. It's just an ammeter. A galvanometer just means it can measure in both directions. So that is actually what this one is. The needle is observed to move in one direction. Oh, so let's just, before we look at the answers, let's just see what's happening. So as it's going in, it's going to try and oppose the change in flux again. So while we're moving the magnet down, we are pushing a north pole into this loop. So this loop is going to create a north pole at the top, a south pole at the bottom. So your thumb would be pointing up, and that means the current in this loop would be going anti-clockwise. Are you getting that? Okay. So that's while it's moving in. But as soon as it's now, gravity is also always going to win. It's not going to hover. Okay, the magnetic field is not going to be big enough to stop it from falling. So now, while it's moving out, so this magnet is now on its way out. But now, if you're looking at the magnet, the south pole is now at the at the top. So it's going to try and pull that south pole back up. So again, we are opposing the change in flux. The change in flux is the south pole moving away. We want to pull that south pole back in. So that means this new magnetic field will be induced or will be formed by a current that will have it will create a north pole there to pull the south back. So that means now if I'm pointing my thumb to the bottom, to the north pole, you will see that your fingers are curling this way. Do you get that? Okay. So as it's going into the coil, there's a anti-clockwise current, and then split second zero, and then as it's going out, there will be so it really does something like this. So it will be either in the one direction and then in the other direction, or it would be in the one direction and then in the other direction. So will look like that, and then it will go away. All right. So you must remember that it's always going to be bigger because gravity is going to win and it is going to speed up, and therefore the time is getting smaller. So the voltage and the current is getting bigger. So let's look at our options. The needle moves in one direction and does not return to zero. Okay, so that is very wrong. The needle does not move again. Very wrong. When will the lead? I'm still wanting at some point a question like this being asked. If this is a when will there be no current induced? Okay, so when you're holding it still, but they're not going to do that. I'm looking for something where they're going to give you a question. It hasn't happened yet. Where they give you a question and there's an open switch or something here, or there's a gap, or there's this loop is not actually connected to a circuit, or there's an open loop. So please remember that that needs to be a closed loop for any of this to happen. And it is a closed loop because it goes going to the ammeter. But if it wasn't a closed loop, then you must just be careful because then no current can flow. So this would be if there is so the change in flux must be zero or an open loop, then that would be zero. Okay, then the needle on the ammeter is observed to be moving in one direction and then returns to zero. Again, no, because it's going to return to zero only after it's gone the other way as well. So then the next one, the needle on the meter is observed to move in one direction, then in the other direction, and then back to zero. So if you think about the answer first, before you look at the options, it should start popping out at you for these multiple choice questions because they do put stuff in there to confuse you. So it's similar to this very first one again. So they do put things in to confuse you, like this one going in the same direction. But if you thought about it first and you know one direction, other direction, then you know it can't be that one. So always think about the answer first before you jump in and read the options. That is the thing with multiple choice. They're there to confuse you. Okay, so these are those graphs I always say they want to ask because it's not a normal generator graph. So again, they're giving you the flux and they say during which two intervals will the induced current in the coil be equal in magnitude but moving in opposite directions. Okay, so what you need to think again is that when you're going from this one to a EMF graph, so to a voltage graph, the voltage graph will be minus the gradient. Because if you're looking at your equation again, then you know that change in flux, which is our y here, change in y, over change in x. So change in flux over change in time is change in y over change in x, because this is flux and that is time, and that is your gradient. But then because of Lenz's law, we have a negative here, and if there are different windings there. So So I should just say almost directly proportional there. And that is why it's the negative of the gradient. So when you go from there to there, it's always the negative of the gradient. So they want to know they'll be equal in magnitude, but looking in opposite directions. So we're looking at equal gradients, but the one must be positive and the other one must be negative. So now we're just going to have to look at where the gradients give us the same value. So here it's 2 divided by 1 for that little bit there. So if we get something that comes down, 2 divided by 1, then it's going to be, that will be our answer because this would be a positive one, positive gradient, which would give us a negative value here. So then here that would be 0. We can just go through it. There it would be 0. Here it will go up, but it's, I wrote over the thing here. For this bit here, your gradient is, we're going 2 up, 2 across. So it's 2. So here it's 2 over 1, which is 2. Here's 2 over 2. So that one will be a little bit smaller. It's positive again. So this line would be negative, but it will be half of what the first one was. This one is going 2 over 1 again, but it's in the same direction. So for that green one, it is the same, but it's going in the same direction, and they wanted them to be going in opposite directions. Now let's look here. Here we're going 1, 2 down, and 1 across. It could be there, yeah, as well. 1, 2 down, 1 across. It could be that one. 1, 2. So that whole line, obviously, because it's one straight line, is going to give us the same gradient. So for this whole bit, yeah, the gradient is going to be the same as what it was for that first little bit. So for that whole time there, we're going to have a flat line here that is the same as this first little bit. And then for that last one, where this is flat, this is going to be 0 again. So the opposite, so they say during which two time intervals will the current be equal? So they don't worry for how long it's running. So that means it's this first little bit. So from 0 to 1 second. So we're looking for that. And it's kind of obvious because there are three options. That's that. Also, start looking at how they sometimes make the answer obvious. It's not going to be this one. So that is just for the people that thought the zeros are something. So can't be that one. So it's between 0 and 1. And then we just need to look, it's for that whole time, all the way from 5 to 9. So it's for that whole time from 5 to 9. It's not just for a little bit in between, it's for the whole time. So the answer is then B. Look out for these in real questions as well. Does this one make sense to you? It's a nice question. Okay, so do you understand the part where the gradient is the EMF? Okay, so when I'm saying EMF or voltage, please remember that if it's in the same coil, if it's in the same thing, so it's not a transformer, then we can say, or the same resistor or the same load or anything like that, then the voltage is directly proportional to the current because of Ohm's law. So the gradient of the flux graph will always give you the EMF graph. And if it's the same resistor, it will look the same as the current. So this question was asking about the induced current, which is the same, going to look the same as the voltage. Doesn't have to have the same value. Okay, so yeah, as well, from the flux to the EMF, they're not going to have the same value. They're just going to be like directly proportional because remember, in the equation, there could be still an N. We don't know what N is. So they're not equal, they're just directly proportional. So because we know that change in flux over change in time is the gradient, whenever we want the EMF graph, we can look at the negative of the gradient. Are you happy up to that point? Okay. Then we need to look, what is the gradient? So the steeper the gradient, the bigger the EMF. The flatter the gradient, the smaller the EMF. And also because of this negative here, if the gradient here is positive, the EMF here is going to be negative because of Lenz's law. So for that first little bit, I'm actually going to just redraw this one as we go. So for that first little bit, if you look at the gradient, the gradient is positive. So that's the one thing you need to ask yourself. What is the sign of the gradient? So for this first little bit here, the gradient was positive. So we know that my EMF is going to be negative. So I know the line is going to be some year below the line. And because it's a straight line, it's going to be a flat line. Are you happy with that? Okay, so let's just give it a value. Let's say it's x. And you got it by saying 2 divide by 1. So the gradient here was 2 there over 1. So this gradient, change in y over change in x, is 2. And that would give you an EMF that is x. We don't know what it is because we don't know what n is, but it really doesn't matter. You don't need to do calculations here. Then for that second bit there, from 1 to 2 seconds there, because there is no gradient, that means that this value here from 1 to 2 seconds is just going to be a flat line there. Happy with that bit? Okay. Then let's look at the pink one. So for the pink one, it's the gradient there is 4 to 2. So that change in y is 2 divided by 2. So that gradient there is 1. So change in y over change in x is going to be 1. So that means if this was x, that pink one should be half x, but it's still positive. So because it's positive, this one must be negative, and it must be half of what this one was. Does that make sense? Okay, so I'm going to draw it like that. So it's only up to that little point there because I think it changed there. Yeah, it did change there by the green one. So it's only there up to 3. 4, sorry. Where are we now? From 2 to 4. Yeah, from 2 to 4. So all the way to 4. Okay. Then we go into that green line. So for the green line, this was also one of the distractors. Now it's going 2, so it's from 6 to 4. So change in y is 2, change in x is 1. So that one there is again 2, that green one. But, so it's x again, but it's positive still. So that means the line is still going to be negative, and we're going to be back at x because it's the same as what it was for that first black line. And it's going to be that up to 5 seconds. Happy? Okay, now let's look at the purple one. So for the purple one, this whole bit here, the gradient is negative. So it doesn't matter where you get the gradient is negative all the time. So there's a negative gradient, so I know that my value is going to be positive. So I don't know where, but it's going to be a positive line, and it's going to be a positive line all the way from 5 to 9 because that gradient is a straight line. Oh, that line is straight, so the gradient stays constant the whole time. So all the way from 5 to 9, I'm going to have a flat line all the way here to 9. So now I just need to look what is the gradient. So you go and calculate the gradient or just in your head for that whole bit. So you can do it for a piece, that's what I did earlier, or you can do it for the whole bit, which is maybe better. So you're going to say, okay, 1, 2, 3, 4, 5, 6, 7, 8 there. So change in y is 8. Change in x is 1, 2, 3, 4. So change in y over change in x for this bit here is 2 again. But now it is because it's minus 8, it's minus 2. So because this gradient is negative, I'm going to have a positive line. We already said that. And it's 2. So the size is the same as what it was for the first black bit, but it is now in the opposite direction. So now it's there, but it's again back to X. Does that make sense? Okay. So for there is another option they could have used. They could have said there's green and that whole big purple. Because but that's not one of the options. Because yeah, the gradient was 2, and for the purple, the gradient was 2, and they are in opposite directions. But there was no option for that green one that was from 4 to 5. So for this little bit here, there was not an option there from 4 to 5. They put that one in there so that the people, for to confuse the people that think, say, that didn't read properly and didn't read the whole opposite thing. So that's why the green one was not correct. Okay. Are you happy with this one now? Okay. Look out for these. They do like asking them. It's always the negative of the gradient. Okay, let's look at this one. Metal ring on a table. South pole is moving down into the ring. Current is induced. Closed ring, so there can be a current induced. So again, now this time the South pole, oh, so this time they are asking us for the direction of the induced current. So yes, we are pushing a south pole in. So if we're going according to Lenz's law, the induced current, so that's the new, in this new loop, the induced current will form a new magnetic field to oppose the change in magnetic flux. Okay, so the new magnetic, we're pushing a south pole in. So what will oppose that? What must we form at the top? South pole. So you did write it correctly there. So I'm going to have a south pole at the top and I'm going to have a north pole at the bottom. And they're saying it's moving towards the ring. So they're only caring about the bit where it's towards the ring. So now you're going to use your right hand again and you're going to point your right hand towards the north pole. So here's north, here's south. You're ignoring the magnet because you don't care about the magnet. You care about the new magnetic field. So you're going to point your thumb in the direction of that new magnetic field, which is at the bottom, and then you should get that the current that is going to be induced is going around this way. I see arrows in both directions. Are you getting that now? Okay. So when it's a straight conductor, you must hold the wire with your thumb in the direction of the current. I actually have a page with all the hand rules on it. I'll send you that. It's just all the hand rules on one page. So you hold your wire in your right hand, your thumb is the direction of the current. But when it's a loop like this, your thumb points to north and your fingers shows you the direction of the current. So it kind of swaps. So yeah, just ask yourself, is it a straight conductor? Then it's the thumb is the current, but I'll send you that page. I hope I can find it. I actually forgot I made that. But yeah, it was also because the kids at Bolu always used to get confused with all the different hand rules, and I made that sheet with all the hand rules on it. I'll send it to you. Yeah, so you're getting it now though. Okay, so it's going around like that, like that, like that. Perfect. So it's going to be clockwise. Oh, so they're telling you reasons as well. So it's one of these two because the flux is increasing, because the flux is decreasing. So this time the flux is increasing because it's getting closer. But that's kind of a weird question because yeah, it's not a constant field. The field is changing, but it is increasing. So the answer would be you see, this is very similar. They like these. Similar to that one we just had. So again, here they're asking for during which time interval will the EMF induced be a maximum? So EMF induced, again, is going to be the negative of the gradient, because again, they're giving you a flux graph. But when they say the be a maximum, you don't really care about negative or positive. You just care about the size of the EMF. So you just want to look at where is the gradient the biggest. So you're actually just going to look for the steepest part. So where is it changing the quickest? So let's look here. So here we're going 1, 2, 3 over 2. So for there, the gradient is 3 over 2. Here the gradient is 0. Here the gradient is 1, 2, 3 over 1. So that's already bigger than that one. So 3 to 4 seconds is winning so far. And here it is 1 over 1. So this one is definitely then going to be the winner because it's the steepest one. And that would give you then from 3 to 4. Does it make more sense now after having done that other one? The gradient is only 0 here. The flux on this graph is never 0. Oh, you mean, oh, are you thinking about where it's changing? Yeah, when, when it's passing 0, yeah. Okay, so please, that sentence that you just said only ever works for sine and cos graphs, never for these. So it's only when you have a constant thing like this. Because if you are looking here, the change in flux is 0 because it's a flat line. But here, because it's still changing, the change in flux is not 0. And that is why when you have these graphs, when you have the sine and cos graph, yeah, where the flux is a maximum there, the change in flux is 0. And that's why the EMF would be a minimum there. So it only works for these graphs. So the only time you can say that when the flux is a maximum, the EMF is a minimum, is when you have these generator graphs, not for any other type of graph. Does that make sense? So you're still looking at change in flux, not really at the value of the flux. You're looking at change in flux. So here, there is no change in flux. So the change in flux is 0, and therefore the EMF will be 0. So there, where that value there our EMF will be 0. But yeah, where the flux is 0, the EMF will not be a maximum because there's still you need to look at the steepness of the line. I can see the confusion though. It's again these graphs that are causing the drama. Telling you they should just take them out. But because the normal generator gives you these graphs, they will always be there. So, and you most often will get them. But these are always thrown in multiple choice, or often thrown in multiple choice question to test the concept of the gradient. Okay, question 4. Okay, I'm going to ask this question again. How do you know that it's a motor? Nice. So actually, they're asking you that in the first two questions. So it's changing electrical energy into mechanical energy. Perfect. And the only reason why it has a split ring commutator is because is a DC motor. And in a DC motor, we need to change the direction of the current every 180 degrees to keep the motor rotating in one direction. Okay, just make sure you know that. Then give a reason why section BC does not experience a force while the coil is in the position shown. So if you are looking at BC here, the current is going, let me just get the direction right. Okay, so from the battery, this is my positive and this is my negative. So the current's coming here, 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 here. And in that one there, the current is going in that direction. And if you are looking at the magnetic field is going in that direction. So we have a current going to the right and we have a magnetic field going to the right. So they're going in the same direction. Now you can do the maths, or you can just show here that you can just say they are in the current and the magnetic field is in the same direction. But if you look at your equation that says F equals B I L sine theta, for this little part here, L I is going in that direction, B is going in that direction. So for that length of wire there, AB, or what is it? BC, sorry, for BC there, for that length of the wire, the angle is 180 or zero. So if you look, but in our case, it's from north to south, so the angle is zero. So this is going to be sine 0 degrees. And what is sine 0 degrees? Zero. So that means because sine of zero, so it doesn't even matter what these things are, because sine of 0 degrees is zero, the force is going to be zero as well. So now if you remember your slap rule or Fleming's left-hand motor rule, these things must be 90 degrees to give you a max. So if this, for this wire here, this wire there, the current is going in that direction, so that's my current, and my magnetic field is coming in this direction. It's my magnetic field. So here they're going 90 degrees to each other. So because the current and the magnetic field is 90 degrees to each other, then sine of 90 is then 1, and that gives you the maximum force that it will experience if it's 90 degrees to each other. Does that make sense? Okay. The rest of this question, was it fine? Is it just the one that you marked? Okay, because K will be the brushes, that will be the split ring commutator, and remember that you must be able to state the function of the split ring commutator. And don't get the name confused. Okay, this was electrostatics. Was this your school's trials? Okay, then maybe they're not using the cluster. If it says, you can also look at the front of this trial paper if it said set by cluster, or does it say set by your teacher? Okay, so then you're not using that cluster's papers. I don't know which schools are actually in that cluster. I just know it's a lot of schools from that area. Um, the spheres. Okay, so the first thing with the magnitude of the force, we just have to remember that it's the same again. Sorry, I just want to make, oh no, too big. Okay, two small identical spheres, insulated stands, carry charges of Q and Q, 3Q. When the centers of the spheres are distance d apart, they experience a force F. Now, okay, wait, let me just read the whole thing. On each other. A is a point at a distance S from the positive one. Okay, so that's where A is in the net electric field. Okay, the spheres are made to touch. Okay, I was hoping not, but they don't do that. So at the moment, remember, the force is F. So if they were asking the force of A on B, please remember that it's again the same as with the magnetism. Force on A, force on B, same thing. But now they're going to touch, so the charges are going to change. So that's that very first thing in the electrostatic fields section, where you have to be able to share the charge. So if this one is Q, 1Q, and this one is, and it's minus, this one is plus 3Q. When they touch, they're going to share that, remember. So we're going to have a minus 1 plus 3, and then we're going to divide that by 2. So minus 1 plus 3, we end up with a 2 plus 2. Divide by 2, so that means this one is now plus 1, and this one is now also plus 1. You're happy with me up to there? Okay. Now, this is where the trick comes in. You need to look, what is the change? This one was 1. Ignore the signs because we're looking at the size of the force because they say the magnitude of the electrostatic force. We don't care in which direction it is because we'll get to that when we look at the field. Okay, so the magnitude of the electrostatic force. This one was 1 and now it is 1. So it doesn't matter. We're only looking at the size. So if you're looking at the equation that says F equals K, Q1, Q2, and it doesn't matter if you use, it's the only place where it doesn't matter if you use small or big Q's, over R squared, we are looking at what has changed. It was F, because they tell us it was F originally. Now we look at what has changed. This one went from 1Q to 1Q. So actually, if we say that this is Q1, it didn't change in size. So Q1 is still Q1, K is still K. They told us that they take them to the same positions as they were before, so R is still R. So actually, if we're calling this one Q2, the only thing that changed was Q2 because Q2 went from being plus 3 to being plus 1. So it's now a third of what it was. Are you with me there? So that means the only change that happened here was that Q2 is not Q2 anymore. It's now a third of what it was. So that means the force, because this is an equal sign, the force will now be a third of what it was as well. So the answer is going to have to be a third F. Oh, they were silly because I never understand why they do these because there's only one. Once you've done F, the rest, this one doesn't matter. So we have F already, so that means that a third F is what it's going to be. But let's just check the electric field strength because we need to talk about that as well. If you're looking at the electric field strength, you must always pretend that you are a little positive sitting at that point. So there is no charge, but if you're pretending that you're a little positive sitting here, you need to think, okay, what field do you experience? You experience a field due to this one here, due to the 3Q, which is now actually just Q. Okay, but they're just caring about the direction. So this is positive 1 now, and this is positive 1 now. So you experience a field because of the positive 1, but the field direction is always going to be away from a positive. But that's why I say if you pretend that you're a little positive, you will always be pushed away from another positive. So you are experiencing the field away from the positive, which means it is to the right. So that made sense because it is 1F and it is to the right. So the answer is B. Happy? Okay. So the only thing that confused people is this when it's changing from 1 to 1. Just remember it hasn't changed, even if the sign has changed. The size has not changed. Okay. 3 charges placed in the triangle. Which of the following? Oh, the direction of the net force. Okay, so remember when they're asking about force, you force is always on a specific particle. It's not a point. Field can be at a point, but force must be on a particle. So we're looking at minus q. So what I do is I take that minus q and you highlight it and you draw a free body diagram for that thing. So if I'm drawing a free body diagram for minus q there, I need to think which forces are acting on it. So it experiences a force because of this one, because of this, and this is a plus q, and that's a minus q. So what will a positive and a negative do with each other? Attract. So it's experiencing a force in this direction because of this plus q. So there's going to be a force. So this would be F because of the plus 2Q. will be this way. Then it's going to have another force acting on it because of the other object. So here's minus and minus. What will minus and minus do with each other? Repel. So it's going to have a force away from this one, but it's in the same direction. Oh, I mean, the same size because it's 2, 2. So these two will have equal length. So it will be going this way. Okay, but now remember, when you're doing a free body diagram, that does not give you the resultant. A resultant, when they say the net force or the resultant force, you have to draw them head to tail. So what you then have to do is you have to say, okay, fine, I'm going to do the blue force, and then it's going to be the head to tail or parallelogram method, whatever you want to do. So this will be the force due to the minus 2q. This will be the force due to the minus 2q. So you just draw them head to tail, and then you can see your resultant is always going to be from the start of the first one to the end of the last one. That will be your F net. So the answer should be A. Are you happy with this one? Yeah, you can. It will just, so let's say the one it wasn't 2 and 2. Let's make up one that is not 2 and 2. So for this one, this blue line and the brown line will be exactly the same sizes. So it will be exactly horizontal to the left. But let's make it not be that. That's actually would be a good question. If it was not that, so let's say this one here was 5 minus 5q. Okay, and they don't give you so they just give you the charges like that. These things can still be spaced like this, but they're giving you a bigger charge there. So now if we're drawing the free body diagram, so there's still this force pulling it this way. It's good color. So that pink force pulling it that way is still there. So, but that will be now a smaller force than this one because the repulsion force is now because of minus 5q and this is plus 2q. So the negative one now will be a longer line up. So now if you go and draw your head to tail, even if you don't have sizes, if we go and draw our head to tail and we draw the pink force first, the pink force is going to be there, but then this one is going to be a much longer line. So that means this one I'm going to draw like that. So that would now be my blue force. So can you see that my net force now is going to be pointing up in that direction? So that would now be F net. But because they were the same sizes, it ends up in the same place. But then if it was like this, the answer would be D. So it does matter. Did I answer your question? Because I just drew them head to tail. So when you're getting a net force, always take your forces and you're not allowed to change the direction of those forces. So so we can even put an angle in here if this was a real question and you had the angle. So this angle there, theta. When you draw the head to, when you draw the your head to tail. So if I draw my pink one, I need to start here from the vertical, and that theta there must be the same theta it was there. So there is going to be my pink theta. Then the blue line, because this charge is bigger. So let's say this is F here. We work it out to be an F. That's F. But then this blue one, I could make it 6 to make our values easier for a multiple choice question. If this is 6q, then this is 6 times bigger than this force. So this, 3 times bigger than this force. So this will be 3f. So this line that I'm going to draw for the blue line, let's say that angle there is now uh, it will still be the same angle because if they're placing them in the same triangle, you would still draw from the vertical there and that angle would still be theta. And then you would draw a line 3 times as long as this one. So 1, 2, 3 times as long. Just a sketch diagram. So this will now be 3F. So that line there is much longer. So now if you go and get your net force, it's always from the start of my first force to the end of my last one. So that there would now be F net. Does that make sense? Yeah, it's the same thing because all I'm doing is remember when you're doing the parallelogram, you're taking this pink one and you're putting it there. Let me see if I can copy the page. Yeah, I can. Oh no, it's not moving the diagram. I thought it was going to move the diagram as well. Oh, it doesn't matter. So when I complete the parallelogram, your pink line will be completed here at the top. So you would have your parallelogram going up there, and then your blue line would be here. So yes, that would be the parallelogram. So your diagonal would still be your net force. Yeah, we don't actually, they've taken parallelogram method out of the SAGs, but it's the same thing. Parallelogram method and head to tail is the same thing. You just have to draw them one after the other to get your net force. Same thing. Does it make a little bit more sense now that it's going up? Okay. So the only reason why this one was A was because the two Qs were exactly the same. Oh, another one. So this is similar to that one. But now they are not. Maybe let's see what they are giving us. Oh, yeah, they're just going up, down, left, right. Yo, I'm liking this question. I'm going to put this in a paper that we just made up because I haven't seen it asked like that before. Um, 3 point charges are placed in three corners. Again, the triangle is given. Which of the following vectors best represents the direction of the resultant force exerted on A by B and C? So again, we're going to highlight A and we're going to focus on the forces acting on A. So you can do it in the diagram rough again. So again, this is Q and Q. So the force between 5 and Q is going to be the same as the force between 5 and Q. This time it's negative and positive. So what will they do with each other? Attract. So there's going to be a force towards B from A. So A will experience a force this way. So this will be the force of B on A going that way. And then there will be another force. So going this way. This will be the force of C on A going that way. But because the sizes are the same, those two forces are going to be exactly the same size. So now when we draw them again, you're drawing head to tail or parallelogram method. So no change of direction. So you're going to draw from there. You're going to draw it this way. So that will be the A on B. And then let's do it parallelogram method this way. So you can draw that one there. Not very straight, doesn't matter. So that's my purple line. Then, so this is F, C on A. And then we're going to complete that parallelogram, F, B on A. But you'll see now parallelogram is the same as if I didn't draw this one there, but from this one's head, I started the purple one. So now I'm going to start here and I'm going to draw, complete the parallelogram. So that's my purple line there. And then I'm going to complete that parallelogram. That's my pink line there. So if I was doing head to tail, I wouldn't have one of these sides. I would either have this side or that side. It doesn't matter which one you go first. You put first. So now they're pulling like that, and that's my parallelogram. So my resultant would be from the start of the first one to the end of the last one, or the diagonal of your parallelogram. And again, because they are the same sizes, it will go that same distance to the right or to the left as it goes to the right. So my answer would be D. Does it make more sense now? Okay.